Good evening, all of you. So, today my name is Anil Yadav, and I am here to take the tutorial 8 on fundamentals of semiconductor devices. So, today we are going to discuss about the MOSFETs. Okay, today we will discuss about MOSFETs. So, in previously we have discussed about the MOSFET. So MOSFET stands for the metal oxide semiconductor capacitor. So how it is different from the metal parallel plate capacitor is, in parallel plate capacitor both the there are two metal plates, and in between them there is a dielectric. Okay, so the charge at the metal place is can be at the interface. So that when we apply a field, so when positive here, negative here, so what will happen is the positive charge will be at the interface, at this interface in between the two parallel plates, and the negative charge, equal negative charge will be at this interface. But in semiconductor what happens is there is a dielectric constant of the semiconductor. In but metals, the dielectric constant is infinity. Okay, so that's why the charge is at the interface. Charge resides at the interface in the metal, at the metal. So but in the semiconductor it is there is some dielectric constant, and we when we dope say this is a p-type doped semiconductor, p-type doped semiconductor. So whatever the majority or minority carrier, the charge is okay. If we apply a positive bias here at this interface, so what will happen is so initially so Na is the doping, Na is the doping here, Na is the doping. So what will happen is Na will turn into Na okay, minus plus whole. Okay, so this will, so there will be, so the atoms at so the dopants will be dissociate in Na minus plus holes. So that the charge at the interface, that will be because of the immobile ions initially. So there will be regions that we have already discussed in the previous lecture. So they will be initially, that will be the depletion region will be there, and then accumulation, depletion, and inversion regions will be there. So we will explore how these regions are used for the MOSFETs. Okay, so how so as a, we can use MOSFET as a switch. So we will discuss the working of the MOSFETs in this lecture. What we have discussed recently was the MOSFET. In MOSFET is, this is the gate, okay, and this is the dielectric, and this is the this whole part is the MOSFET. This part is the MOSFET, and this is the p-type semiconductor, this p silicon. Okay, when we apply a positive bias here, so there will be a creation of the inversion layer at the interface. At this interface there will be a very thin layer of electrons at this. Okay, so inversion is so this channel, we call it channel. So this channel, as this channel is created, okay, so as we apply the positive bias at this point at gate. So in MOSFET what we so this so there is a source, there is drain, and in between them there is channel. So these source and drain can talk, can be current in between this source and drain, because of there is a channel. This is N++ doped, this is N++ doped, and there is a channel of the electrons in between these source and drain. So when we apply a field in between the source and drain, what will happen is there can be there will be a drift of the charge carriers in between the source and drain. So say let us see, we have applied a positive bias at the gate sufficiently, so which is VG is greater than VTH. Okay, VTH. So what will happen is, so this will create a channel just below the just below this gate. Okay, below the gate, in between, below the gate at the interface of the semiconductor and the dielectric. So this channel is of there is very high density of the electrons at this channel. This channel is very thin, say 1 to 2 nanometers of the thickness. Okay, so and this channel connects the source and the drain. So this channel can only be created with the application of the bias at the gate. So if we remove the gate bias, or the gate bias is not sufficient to invert the channel, or to create the mobile charge carriers to at this point, to invert the channel, to create the electron, very thin sheet of the electrons at this point. So there won't be any connection in between the source and drain. Okay, so as we have applied the sufficiently positive bias at the gate, and now if we this source is grounded, or this source is grounded with the substrate most of the times. Okay, so we will see the how this substrate bias will affect the device characteristics. So and in this one, okay, so first I will show you how where is this MOS cap. Actually, this is the MOS cap, as we have discussed. So so in the Venn diagram, so okay, in the Venn diagram, this is the oxide layer. So this is the metal Fermi function, and as we applied the positive bias here, so what happens is the what will happen is that at the metal, at the semiconductor and the oxide interface, at the semiconductor and oxide interface, bands will bend like this. Okay, bands will bend like this. So there will be a this in this region there are so many electrons, there is a sheet of electrons. So this whole part, this front part is this one. So this is metal, this is oxide, and this is semiconductor. This front part I am showing you. Okay, so if you cut this, if you take the slices of this device like this, okay, like this, if you cut this device like this, so you will, every time you will get the same thing. Okay, you have applied the positive bias, everywhere the channel is created. So this the depth of this G depth is nothing but whatever is the, okay, what to say, okay, yeah, this G depth. Okay, and okay, just a minute, I will remove this thing first and then we'll tell you. Okay, so okay, yeah, so okay, so what this thing that I show you, there is a creation of the channel. Okay, there are so many electron, or we can say the electron gas at the interface. The electron gas at the interface is the channel. Okay, this is the thing that you need to know for the function of for the working of the MOSFET. Okay, so in this case, what we can see is okay, and next thing is so this source is highly doped N++ region, highly doped N++ region. We cannot dope it P++ region because it won't connect. So N++ region is the highly conducting. Okay, so these so that's why we dope it with the highly dope with the negative impurity. Okay, and which connects, so whatever the channel is there, we dope it with that one only, or we can say. So, and another thing is there will be a depletion region over this, so that will reduce the that will reduce the crosstalk, or reduce the flow of the current through any means, or through the, if we apply the bias here, so that will reduce, not the positive one, we will apply the negative bias, we can apply to reduce the threshold voltage here. So we can apply the negative voltage here. If we apply the positive voltage, what will happen is, okay, just a minute, I will, someone wants to join the meeting. Okay. Hello. Hello.
Hello.
Aditi, can you turn off your mic? Yeah, thank you. If you have a question, you can ask, or otherwise, just keep it turned off. Okay, so in this one, where were we? Okay, so so this is highly doped N plus plus region, and this is highly doped N plus plus region. In between them, there is a N channel here, and above this N plus plus doped region, this is metal. This is metal, so that we can take the connection. Okay, and another, this is the gate, which is metal only, and below that gate there is channel. The channel is created below the gate only, as we apply the positive bias here, so it will attract the electrons here, or attract the electrons, or actually it doesn't attract the electrons, it repels the holes. Electrons are in this region are generated, as we have seen in the MOSFET. Electrons are generated in the depletion region only. It depletes the majority charge carriers. Uh, it repels the holes from this region, as we apply the positive charge, positive potential here. Okay, so and so if there is a small region which overlaps with the source and drain, which is because if this doesn't overlap, or if just take in this thing, so if the gate was still here, so there won't be any channel in this region. Okay, so if just suppose the gate was still here, this much thick, this much width of the gate would be, so this region wouldn't be inverted, so there wouldn't be a proper connection in between the source and drain. So this gate should, a small part of the gate should overlap with the source and drain. Okay, so that we can make sure there a proper channel is created properly below the gate, that can connect the source and drain. Okay, and there are different types of the this MOSFETs: N channel MOSFET, P channel MOSFET. This is the enhancement mode type of the N channel. In enhancement mode is the when there is the MOSFET is off, when we don't apply a voltage. Okay, MOSFET is off when we don't apply voltage, it is normally off. Okay, in depletion mode MOSFETs, what happens is we need to apply voltage to turn it off. Okay, we need to apply voltage to turn it off. We need to apply a negative voltage to turn it off, and it is normally on at 0 voltage. Okay, this is N channel. In N channel, when we apply a positive gate voltage, it creates the N channel, or it creates a channel just below the gate, which is full of electron or electron gas. Okay, so when we apply the voltage in between the source and drain, there is a conduction of the electrons through the channel. Okay, in P channel enhancement, okay, enhancement type is for both. Enhancement means it is normally off when we don't apply a voltage. At 0 voltage it is off. Okay, at 0 voltage the current is 0, but in zero gate voltage actually. Okay, 0 gate voltage, so the threshold voltage in this enhancement mode N channel is positive. Okay, the threshold voltage is positive. But in in depletion mode, the in depletion mode N channel MOSFET, this threshold voltage is negative. So at zero voltage it will be on. So when we apply drain voltage, we apply a voltage at the drain, so there will be a current, okay, at zero gate voltage only. So we need to turn it off, we need to apply voltage in the negative. Okay, so this happens when the flat band voltage is so, or say that say that metal semiconductor work function difference, because of the metal semiconductor work function difference, as if metal work function is very high, if metal work function is very high, so this will be kind of the N channel depletion mode type of. Okay, so if metal work function is very less, and in this case, and it is P channel, P type, so in this case the VTH is positive. Okay, in this case, so in enhancement mode it is normally off, but in depletion mode it is normally on. We need to apply at voltage at the gate in the reverse direction to turn it off. Okay, so okay, so this is the front view. This is, we can say, the top view of the our MOSFET. Top view, this is the gate, this is the source, this is the drain, and this is the P type substrate. Okay, so here it is very short actually, so N plus plus is not too deep. This N plus plus is not too deep in the G direction, in the X direction actually. Okay, this N plus plus is not too deep, because if it will be deep, so there will be a crosstalk, or there will be some other effects will come into picture. Okay, and okay, this is the gate. So this is the bend diagram. Okay, this is the bend diagram when we haven't done anything, we haven't applied the gate voltage. Okay, so we haven't applied the gate voltage. This region is a N type. Okay, this region is N type, this region is N type. Okay, and this region is P type. Okay, we haven't applied any voltage till now. Okay, so this junction. Okay, now let us see the junctions one by one. So this is N plus, this is P. Okay, this is N plus, this junction is N plus P junction, N plus P junction. Okay, this junction is P N plus junction. Okay, so there are two junctions back to back, two PN junctions back to back. Okay, this junction and this junction. So this is N type. So the Fermi level is close to the conduction band here. Okay, in this region. And this is N type, N plus plus. So the Fermi level, this dashed sheet. Okay, this dashed sheet, we are taking the 3D model. So this dashed sheet is nothing but the Fermi level. Okay, Fermi level is constant throughout the device. Okay, this is Y direction, this is the D depth side is the X direction, and okay, and this is the field, or this E direction, or the actually it is the G direction. Okay, so this is the G direction. Okay, so now and this other thing, this okay, this light black, this one is nothing but the intrinsic Fermi level. Okay, intrinsic Fermi level, the distance between this is the intrinsic, so there won't it will follow the conduction band and the valency band. Okay, and so in this region, now as we apply the gate positive voltage at the gate, what will happen? Okay, so what will happen, so as soon as we apply the positive voltage, so it will bend the band at the interface. This is the interface. Okay, this is the interface that we have seen in the MOSCAP. Okay, MOSCAP. So this interface, so there will be a band bending at the interface. Band will move band will move downwards as we apply the positive voltage at this gate, as we apply positive voltage at gate. So band will move down at this junction. Okay, because it has at the junction, if we apply vg, we are applying vg is greater than vth. Okay, as we apply vg greater than vth, so there will be electrons at this interface. Okay, so this Fermi level, the distance between the Fermi level and this conduction band. Okay, so this is Fermi level, this is the conduction band, so this distance will decrease, so the Fermi level won't move because this is at equilibrium. Okay, so at steady state or the equilibrium, we say when we apply the gate voltage, so this conduction band will move down, and the distance between this or not the gap, not the distance. Distance is a special word. So the gap between the Fermi level and the conduction band will decrease. Okay, so that there will be an electrons at this point. Okay, so what will happen? So this is vg is greater than 0. Vg is greater than 0, so this at this point, as we have applied a positive voltage at this point at gate, so at this point you can see this is the Fermi level, the intrinsic Fermi level, and this is the Fermi level that after the this is the Fermi level at equilibrium. Okay, so or after the doping or whatever, so because of the charge carriers at the interface. Okay, so this Fermi level is in the above half. Okay, this Fermi level is in the upper half, so this becomes the charge carriers. There is then inversion of the channel. Okay, from p type it has been converted to the n type. Okay, n type in this region. So this is the channel, this is the source n plus, this is the drain, and there is a channel in between the source and drain, which is which we have electrons in between the source and drain. So when we apply the voltage in between these two, there will be a drift of the electrons in between source and drain. Okay, as because of the electric field in between the source and drain, there will be a drift component of the current. Okay, so this n channel connects the n plus region, two n plus regions, which are the source and drain. Okay, so now what we will see is okay, now vg is greater than 0. Vg is greater than 0, we have created the channel. Okay, this indicates vg is greater than 0, but only vg greater than 0 won't give us the conduction in between the source and drain. Vg should be greater than 0, as well as Vg should be greater than the threshold voltage. Okay, the threshold voltage, that 2 phi b phi f. Okay, that we have already read, that 2 phi f should be Vg greater than 2 phi f. Okay, so then only there will be a creation of the channel at the interface. And Vd greater than 0, we are applying the potential at drain, so it will lower the band at the drain side. Okay, this will go down. Okay, this side will go down. Okay, so okay, another thing, there is when we apply the drain voltage, there is a depletion region, or there is a band bending. This will affect the band at this conduction band here in this region. Okay, or in this region. So that we will come when we will see the drain induced barrier lowering. So okay, so just look at this point. There is a gradient, or we say gradient in the conduction band. So there is a field. Because of the applied field, there is a gradient in the conduction band at this junction. Okay, so now we will see how. So this is the depletion region. So this is the depletion region. Whatever comes at this junction will be swept away. towards the drain side. Okay, electron will, whatever the electron at this point will come, it will be swept away. So that we will see when we will see a short channel effect also. Okay, and another thing is huh. So as one junction is more reverse biased, because this, at this junction we are applying the field, so this applying the positive potential at this junction, so n plus we are applying a positive, so it will be reverse biased more, so depletion region at the drain side will be more than the depletion region on the n side, because n plus on the source side, because this is grounded only. So whatever, it was always in the equilibrium position only as it was before. Okay, so now huh. Now we will see the basic working. So this was the this is the top what we say, this is the top view. Okay, this is the top view. So now this is the top view. Now we will see how the okay, now we will see the now we will see the working of the basic working of the MOSFETs. Okay, so that we have seen in the top view, and this is the top view. Okay, now and this is the side view, this is the n plus, and this is the source, and this is the drain. And when okay, as we have applied the positive voltage at gate at this point, as we have applied, and which is greater than the VT. So why I am focusing on the VT? It should be greater than VT, then only this channel will be created, then only there will be inversion of the only there will be an inversion of the carriers. Okay, it was P type, this was the P type. Okay, so as we apply positive voltage here, so it will repel the holes from the junction. So there will initially there will be a depletion region. So if you can see that there is a dotted line, that dotted line is nothing but the depletion region. Okay, this is the width of the depletion region. As we go above the threshold voltage, then there will be an inversion of the charge carriers. So the inversion happens when this is the Fermi level. So when the conduction band, this is the till here there will be a depletion region. When we go below this point, when we go below, this is the Fermi level. Okay, EF. When we apply more and more voltage at positive voltage, so there will be more band bending at the interface of the semiconductor and the oxide, or the dielectric. So more is the more at this point. Okay, just a minute. So there will be band bending. So and there will be more and more electrons at the interface, and these electrons are nothing but they are creating the channel in between the source and drain. Okay, so and now as we have applied a very small drain voltage, we have applied a positive drain voltage at this junction. So electrons will move this side through the channel. Okay, so electrons will move. Let us suppose that this is a perfect rectangular shape. Okay, so this is a perfect rectangular kind of shape. Okay, this is the thickness of the channel, and this is the channel length, and this is a perfect kind of so we are not taking the pinch off currently. So when we because VD is very less than VD saturation, and which is less than the VG minus VT. Okay, so at this point so this can act as a resistance. So there is this can act as a conductor kind of thing. Okay, this can as a kind of conductor which is connected at the two terminals, which is one is source, one is drain, and there is in between there is a kind of wire, nothing, just or a sheet, metallic sheet kind of thing. So what will happen is when we apply a field, so there will be a conduction of the charges. Okay, so there will be a flow of current, and that flow of current will be linearly dependent on the drain voltage. So this Vd should not go beyond. So when we vary the Vd, this voltage between the source and drain, so there will be the current will rise linearly, as you can see in the graph. Okay, so the current will, but it won't rise, it will rise linearly till a certain amount of the current. Okay, so till a certain amount of the voltage we apply. Okay, so and now, so but what will happen if we apply a voltage which is this Vd is equal to Vd saturation. So Vd saturation is nothing but this saturation voltage is equal to Vd is equal to Vg minus Vth. Okay, Vg minus Vth is nothing. The Vg minus Vth is the gate overdrive. Okay, whatever the voltage we are applying extra after the creation of the channel. Okay, the channel is created. Okay, the channel is created at Vt. Okay, so whatever the voltage we are applying extra after the threshold voltage, that will increase the extent that will increase the number of electrons in the channel. Okay, the channel will be there will be more number of electrons, the current will be more. Okay, just a minute, someone wants to join, so let me check. Stay in call. Okay, let me check. Huh. Okay, now if this is the gate overdrive. Overdrive means whatever the voltage we are applying above the threshold voltage, so that will increase the number of electrons, the Qn, the quantity Qn will increase. So more is the charge density, more will be the current. Okay, more will be the current. So okay, this is the Vg minus Vt. Okay, the more is the gate overdrive, more is the current. Okay, more is the gate overdrive, more is the current. So but so, so and this channel will be will okay. So the difference, as we have seen in the MOSFET, so in MOSFET there was no this source, no drain. Okay, so it this channel that was inverted was kind of a rectangular. Okay, but because there was a 0 volt, this was ground, this terminal was grounded, and this terminal we are applying a positive voltage, so the channel was created everywhere. Okay, equal amount of the voltage difference was everywhere. But at this point, as we apply a positive voltage here and positive voltage here, at positive voltage at the drain and positive voltage at the gate. Okay, so at positive voltage at drain and positive voltage at gate, so the voltage difference between the gate and drain is very less. So there won't be any channel in between at this junction. Okay, there won't be any channel at this junction. So and so the channel in this in between the gate, in between the source and drain, will be like a triangular region, like a triangular region, this kind of. Okay, because when we apply a source voltage between source and drain, the voltage at source is 0 and at is Vd. Okay, so there will be a voltage drop in between these source and drain. Where the voltage will drop? The voltage will drop in between the channel only. Okay, and Vd, there is a drop of Vd in between the channel, so there will be a voltage Vx at this point. Okay, so V dash at this point. So the whatever the voltage difference in between the at this point and Vt, so the channel will be created accordingly. So as we are assuming there is a linear a drop in between the source and drain, so there is a linear dependence of the this will be a kind of a triangular region will be there. The triangular channel will be there. Okay, so if we apply more and more drain voltage, so this will the pinch off region, this is the pinch off region at Vd is equal to Vd saturation. Okay, so or Vd saturation is nothing but Vd saturation is equal to when we apply Vg minus Vth, Vd is equal to Vg minus Vt. Okay, this voltage is the Vd saturation. When we apply this much of voltage, so when we apply this much of voltage, so the channel will be pinched off at the just at the junction. Okay, just at this junction. So as we apply, Vd is greater than Vd saturation, so then this pinch off region will move, pinch off point will move towards the left. Okay, so whatever the voltage we apply in between the Vd in between the source and drain, so that won't increase the current. Okay, so there will the current will be constant in this region, in this one, because whatever the voltage, whatever the electron at this junction, that only will be swept away. So now the current is limited by the number of electrons at this junction. Okay, so the current of is limited by the number of electrons at this point which are swept and does not depend on the on Vd saturation. So at this junction, these electrons will be governed by the gate voltage. This is highly reverse bias junction at this point. So that is why this is the here is the diffusion current, and here this in this region this is the drift current, and in this region this is the diffusion current. No, this is also a drift current only. Actually, sorry. This is the drift current only. That is because of the reverse bias PN junction. That is because of the reverse bias PN junction. Okay. Now, so that the number of electrons at this junction is governed by the Vg, whatever we are applying the gate overdrive voltage Vg minus Vt. So more is the gate overdrive voltage, more is the current. Okay, this region is the linear region which is after the pinch off. When the pinch off, this is at this point when the pinch off happens, this is the saturation voltage. Okay, and this is the point when the saturation happens, and after this whatever the voltage you apply, the Vd you increase, there won't be any effect on the current for a constant gate voltage. Now, so there are some things that you need to learn. So what first we will do the current voltage relation. We will establish a current voltage relation which we will assume the gradual channel approximation. Through the gradual channel approximation, we will derive the current voltage relation, and then we will what is the effect of the substrate bias on the threshold voltage. Okay, so now we were doing that substrate is connected to the source only. Source and substrate are shorted and connected to the ground, and then we will see the subthreshold conduction and subthreshold slope. So what is the subthreshold? Before the threshold voltage, what is the current in the device, that we will see. So how the current is increasing in the threshold region. Okay, and then we will see the short channel effects as the miniaturization of things is going on. So we are putting more and more devices in a very very small area. We are doing so we are increasing the density of the devices, we are increasing the density of FETs in the area, in the chip. So there will be effects of the, so how much length, so there will be effect of the scaling. Okay, scaling is, so how we are scaling down the, down the scaling down the device. So we are decreasing the length, the channel length, channel width. How these we are decreasing that these channel length and width to get the a good device. So as we miniaturize the device, so these things will affect. So there will be very less channel effect, so there will be high leakage current. Okay, so these things will come. So the charge sharing between the source and drain, when we decrease the channel length, so there will be, so how this effect comes. So and most of the things come because of the channel length. Okay, so there is drain induced barrier loading also, these kind of things come. So we will see these things. So and first we will see the IV characteristics, how a very simplistic explanation how this this current in what is the relationship between the drain voltage and the current. Okay, so initially assume that we have already applied the gate voltage which is greater than the threshold voltage. So this is the channel, this is the channel that is created below the gate. Okay, so which is almost which we are assuming that it is rectangular. Okay, which we are assuming it is rectangular. So uh, because we are applying VD very small, the voltage applied which is VD is much lesser than the VG minus VT. Okay, VG minus VT is the gate overdrive, or VG minus VT is the gate overdrive. Okay, so so this is approximately rectangular. Okay, so now this can be assumed as a wire, you can assume as a wire or sheet. So we can apply, because this is a very thin sheet of the charges. Okay, so we can assume this as a good conductor, so we can apply Ohm's law here. So IDS, in between IDS is equal to V is equal to IR, right? So VDS divided by R. R is the, R is the resistance between the source and the drain, the channel resistance, or you can see RCH. Okay, this is the channel resistance. RCH is the channel resistance. Okay, from the Ohm's law, we can IDS is equal to VDS by R, and R is nothing but rho L by A. Okay, R is equal to rho L by A. Okay, so the rho will come from the conductance. Okay, this is the rho is nothing but resistivity. So we know the conductivity of the conductivity is given by charge Q into mu n into n. Okay, Q into mu n into n, this is the conductivity. Okay, this is the conductivity. Mu n, Q is the charge on an electron, or charge, and mu n is the mobility of the charges, mobility of the electrons. N is the density of the electrons. Okay, N is the density of the electrons. So N inversion is nothing but the density of the electrons, and T inversion is the thickness of this rectangle, T inversion. Okay, and G is the depth. Okay, channel width. Okay, D is the channel width, we say. G, this G. So this is nothing but the depth of the device. Here, depth of the device in the, when you go into inside the screen, or if we go here in this one, so this is the G. No, sorry, this is the G, this is the G, and this is the channel length, this is the channel length, and this is the G. So the area, so how much is the area is G multiplied by T. Okay, G multiplied by T. So this is the area, and this is the conductivity, and this is the length, the channel length. So the R is given by R divided by R is equal to L divided by Q mu n inversion, T inversion, and G. Okay, so this is given by G L divided by Q inversion. Q inversion is nothing but the charge density, okay, into mu n into G. ठीक है, Q inversion is the Q n x. Nx we are taking it because as here it is 0 and here it is Vd, so there is a drop in between the channel. So the charge density will be different at different points. Okay, the charge density will be different at different points, and that will vary along the channel. Okay, so by definition Qn at V, okay, so Vth at V is equal to Vth. If we are applying this Vd is equal to Vth, so Qn will be 0. So this will be pinch off, right? This channel will be pinch off. So at this junction there will be a 0 voltage. No, there will be a 0 charge density, current charge density, electron density we say. The inversion charge density will be 0 at this junction. So after Vth, the extra charge goes to the inversion. Okay, so yes, after Vth, this Vg greater than Vt, till when we apply Vg less than Vt, so there won't be any inversion. But after the application of the voltage, voltage at greater than threshold voltage at the gate, so there will be an inversion of the charge that we have already seen. And from the parallel plate capacitor, so this is nothing but there is a parallel plate capacitor, there is a sheet of charges at this junction which is always in the metal. Okay, they of the parallel plate capacitor. So this is the metal only, this is the semiconductor, but there is a charge, sheet charge, there is a sheet charge. So this is kind of a parallel plate capacitor. Okay, so in parallel plate capacitor, Q is equal to CV. Okay, Q is equal to CV. This V is nothing but Vd that we are applying. Okay, from here we can calculate the Qn. Okay, because we know Cox, oxide capacitance we know, Vg minus Vth that we are applying, the gate overdrive that we are applying, that we know. Okay, and now id is equal to now we know the R. From here Qnx, from these two we can calculate the R. This one and this one we can calculate the R. Okay, that R we will, when we put here, we will come with this equation. Id is equal to G by L, or we can say W by L. This is G is nothing but the channel width. Okay, this is the channel length, Cox is the oxide capacitance, mu n is the mobility of the electrons, and Vg minus Vth is the gate overdrive, and Vd is the threshold voltage, or no, Vd is the drain voltage that we are applying. But here in this case Vd should be less than Vg minus Vt. Okay, this should be less than Vg minus Vt, less than or equal to it we say, so that there won't be any pinch off at pinch off of the channel. Okay, so this equation will hold for the linear regime. So because as we haven't assumed the pinch off region, okay, we haven't assumed that there is a pinch off in between this. Okay, so we have assumed that this is kind of a conductor. Okay, so if we assume that there is a pinch off, then it will be the channel length will be reduced. So that will be, we will see in the channel length modulation. Okay. Yes, now so now the another thing is the gradual. Now we will derive IV that in a more rigorous way through the gradual channel approximation. So in gradual channel approximation says this the parallel the E parallel is very less than the E perpendicular to the channel. So okay, what we say is okay, E parallel is perpendicular or EX. One second. Okay, yes, EX is okay. Now okay, huh. Yes, E parallel. Okay, so this one, so this voltage okay, the field in this direction, the perpendicular direction or the E parallel, we say E parallel to the channel, so is very less than okay, just a minute, just okay, huh, that is the EX only, no, huh, yeah, okay, okay, yeah, uh, okay, just a minute, huh, this thing I will see once. Okay, so okay, this thing I will see once. So now, so actually, there is a what we see do is so this is the x direction. Okay, this is the ex direction. So ex in this direction, the this field, electric field is less than the perpendicular to the channel. Okay, the perpendicular to the channel. So we have already created, but actually this shouldn't be the case actually. So so what I'm saying is, so the field in this direction, in this direction or in the this direction, which is very less than the field in this direction, okay, in the channel, because so what we are assuming that the electrons are not deviating their path. We are assuming that electrons in the channel are not deviating the path because of the Vg. Okay, so they are moving in this direction. Okay, so the the field in this direction is very less in the channel. Okay, in the channel is less. Okay, now what we will see is now we will in the channel, okay, we have applied the gate bias which is greater than the threshold voltage. In this let us take a very small region. Let us take a region dx, which is okay, the length this is the channel length. Out of the channel length, let us take a dx at very small region, and now let us see the resistance of the channel. Okay, this resistance of the channel is nothing but it will be the one by the conductance. So this is the conductance that we have already seen in the previous one. So this is the conductance which is because of the qn, the charges in this region, qnx at this point, and dx divided by qnx, and mu n, which is the mobility of the electrons, and g is the width of the channel, okay, which is in the depth. Okay, this is the width of the channel. So the total charge carriers qnx, not the qnx, the total charge carriers in this region, which is because of the which is because of the application of the threshold voltage, which total charge qs will be equal to qn, which is the channel, it contributes, this qnx is the charge or inverted charge carrier, the density of the charge carriers, inverted charge carriers at x in the channel, and qd is the depletion charge carrier density. Okay, so depletion, or we can say the immobile ions. Okay. Now, so but what we are interested in, we are interested in the channel charge. Okay, in the channel charge. So now huh, now from the MOSFET, now just recall. So this gate bias, that gate bias we apply. So the voltage dropped will be because of the flat band, and this is because of the semiconductor. No, okay, psi x sx qsx. No, no. Okay. This is because of the flat band, and this voltage drop is in the in the oxide layer, oxide layer, and this voltage drop in the semiconductor layer. Okay. Okay, the voltage that we are applying here is drop in this region and in this region. Okay, so this is what here. So this is the oxide layer, this is the semiconductor layer, and this is because of the Fermi level mismatch in between the metal and the semiconductor. So so there the total voltage that we are applying the at the gate, that will be this one. Okay, so now qs is equal to qsx at any point x, in at any point x, at, let us say, at this point. Okay, at this point qsx is equal to qnx, which is in the channel, and this is the depletion charge. So what we are interested is in the channel charge. Okay, which is equal to the q is equal to c into v. Okay, whatever the voltage here, whatever the voltage here, that we are interested in. Okay, so now, okay, phi is x. So now q this okay, the qn is equal to cox, oxide capacitance, into this psi x, that is the because of the band bending, that is because of the band bending. Okay, this is the psi s, the difference between this difference is the psi s. Okay, this difference is the psi sx, and this is because this is x, we varying with the x because we are applying the vds also. Okay, so the band bending will not be same at every point throughout the channel. Okay, so at this point band bending is more, at this point band bending will be less because of the effect of the vds that we have seen. Because of that's why there is a tapering of the channel, there is a tapering in the channel, that is because of the application of the vds only. Okay, so this psi sx and minus vgb minus vfb. So so this is the gate voltage minus the flat band voltage, and minus qdx. So actually this is nothing, but we have put this, all these, we want to eliminate the qs. Okay, we have through this equation only. Okay, we are eliminating qs. Okay, by this equation. So now now, so phi s x is nothing. Phi sx is what is the phi sx? So this is the threshold voltage plus the vx that we are applying. Okay, this is this psi sx, or what we say, the gap between this is the phi f, between this gap between the Fermi level and the intrinsic Fermi level is the phi f. Okay, so vth is equal to twice of phi f. Okay, VTH is equal to twice of phi f. What we are applying, the VG is equal to VTH plus VD, VTH plus something, some voltage. So VG minus VTH is what we are interested in. Okay, so or this, what we are taking here is the at the threshold voltage only. Okay, so this Vx is nothing but it is the variation in the voltage in the throughout the channel length, with the VDS. Okay, so okay, so this is the QDX, the charge. Okay, the depletion charge, this is the depletion charge. And okay, this is the depletion charge that we are not interested in, but okay, so we need to replace this depletion charge also. Actually what we are we need to eliminate this depletion charge because that is not desired. Okay, so now after solving these equations, you will get this complicated type of equation. Okay, this is the QNX, the charge in the channel, which is varying, this charge in the channel which is varying with the distance x. This is the x, the charge in the channel, how this is varying with the x, the spatial variation of the charge, channel charge. Okay, now from this we can calculate the current, because now we have the charge dV is equal to id into r. Now id into dr. Now dr we have qnx. Just replace this qnx with this equation, and now we have id dx into minus qnx into id dx is equal to minus qnx mu n g dv. So now from the integration we can get the id current, total id, which is dependent on the voltage. Okay, which is dependent on the voltage. So here this is the complicated relation that we get. Okay, the current versus the voltage that we are applying, the gate voltage and the drain voltage, source drain voltage we are applying. So this is the id iv relation that we are interested in, and this is the iv characteristics. Okay, so and this theta here, this theta is nothing but the body factor, which is equal to twice of epsilon qna divided by cox, and it depends on the doping concentration Na and oxide capacitance. Okay, so in our devices, what we most of what so from here we can say, if we have a very high k dielectric. Okay, high k dielectric, c, high k means the c is equal to epsilon by d, right? C is equal to epsilon by d. D is the thickness of the gate dielectric, and epsilon is the dielectric constant. So if epsilon is high, so this is the desired thing for a good MOSFET. So this oxide capacitance should be as high as possible, so that there will be a very good control of the gate over the device. Okay, so this is generally high, and if the doping is also low in the p region, that p substrate doping is low, so what will happen is, so this theta is negligible, we can neglect that theta. So this term, we most of the times we can neglect this term. Okay, what we left is with is the id is equal to g mu n cux by l into vg minus vfb minus 2f. This vfb minus 2 phi f, this is the threshold voltage. vfb plus VFB plus 2 phi f is the threshold voltage. Okay, this is the threshold voltage. Vg minus Vth minus Vd by 2. Okay, so this can be replaced with the threshold voltage. Okay, so Vg minus Vth. And for a linear regime that we have already seen in the while we just through the Ohm's law, we have seen the linear regime. We have established a relation between current and voltage relation through the in the linear regime through Ohm's law. So Vd minus this Vd by 2 is very less as compared to Vg minus Vth. Okay, as compared to the Vg minus Vts, that is the gate overdrive. Okay, so if for a very low drain voltages, okay, which is in this region at the low drain voltages, okay, at the low drain voltages, this can be neglected. This Vd by 2 term can be neglected, and what we will left behind, we will left is this ID is equal to G mu n Cux by L into Vg minus Vth into Vd. Okay, this is the IV relation in the linear regime. So in this region where, okay, in this region that you can see, this is the region of the linear regime. Okay, this is the linear region. Okay, this is the non-linear region. So when this term starts dominating, okay, this term starts dominating, this minus Vd by 2 term starts dominating, then there comes a non-linear region in this region. And further we increase the Vd, so there will be a channel pinch off. Okay, so there won't be any, whatever the voltage we apply Vd, we increase the Vd, there won't be any rise in the current. Okay, so above threshold voltage, this Vd is equal to Vg minus Vth. Okay, this Vg is equal to Vd minus Vth. So here we calculate the Vd saturation. What is the Vg saturation? From this term can be neglected, or this is nothing but equal to the, this term can be neglected. Okay, from this one, from this where is that this body factor or so. So we will calculate the Vd saturation threshold saturation voltage will be Vg minus VFB minus of the volt term. This volt term, this can be neglected, but this is nothing but the threshold voltage only. So this is Vd saturation is approximately equal to Vg minus Vth. Okay, so just replace this Vd in this one, because after saturation we can replace this Vd after saturation. After saturation we just replace this Vd with Vg minus Vt. Okay, so we will leave left behind with this equation ID saturation. Okay, just okay, this ID saturation, the saturation current is equal to G mu n Cux by 12 into Vg minus Vts ka whole square. Okay, and after this in the saturation regime, what happens is Vg is very greater than Vd. Okay, so Vd is very greater than Vg minus Vt. So here after this is the threshold voltage. After the threshold voltage, the channel pinch off is there. Okay, so near the channel pinch off, this gradual channel approximation is invalid. Okay, because of the very high electric field in that region, or the other component of the electric field is very high in this region. Okay, now ID saturates as Vd saturation because after this there is because of the channel pinch off there is however how much ever the voltage we increase there is no effect on the current. Okay, so now qnx is equal to 0 at vd saturation. Okay, that we have seen at this point, at this point this qnx is equal to 0. At this point this inversion charge is equal to 0. Inversion charge density is 0 because of the at vd is equal to vg minus vt. Okay, that's why this is the saturation voltage. Vd minus vt is the saturation voltage, because at this voltage only there is a pinch off, there is a 0 uh, uh, current density, 0 charge density, inversion charge density is 0 at this point. Okay, so now now okay, okay, these are fine things, these are fine. Okay, now let us see the effect of the substrate bias on the threshold voltage. So okay, so initially so okay, this is our this is the source, this is source, this is drain, and this is the gate. Okay, this is the gate. So initially what was the thing is, so this is the p type substrate. Okay, so this we were grounding the source, and we are applying a positive bias or negative bias at this drain only. Okay, so now and initially what we are also doing is we were shorting the source and the source and the substrate. Okay, so there is a 0 bias at this substrate. So whatever so there is a depletion region in between this is n plus plus doped, this is n plus plus doped, and this is p doped. Okay, so there will be a depletion region that will be more over towards the p region only, because of this is less doped and this is highly doped. So in the highly doped region there is a very interface, the depletion region is at the interface only, and in the p region it is more towards the p region, the depletion region. Okay, so as we apply the voltage at this junction, so let us say we are applying a positive voltage, just let us say we are applying a positive voltage. So this is p type, we are applying a positive voltage, and this is n type, so this is forward bias. Okay, so there will be a current flow in between these two, there will be a current flow in between these two, and that current will lead to a leakage current. Okay, so that current will flow through the channel, flow through these two terminals, and there will be a so that's what we do not want. Okay, that's what we do not want. Okay, so there will we do not apply a positive voltage at the p if the substrate is p type, so we can apply a negative voltage so that it can increase the depletion region. Okay, so it can reduce the current, this current also. Okay, so and another thing, if we apply a negative voltage here, so there the and we are applying a positive bias at the gate, so we can modulate the threshold voltage. We can by applying the negative voltage at the at the substrate, we can modulate the charge carrier density, the inversion density at this point. Okay, so at this point we can just modulate that thing. So we can play with the threshold voltage by applying by biasing the substrate. Okay, this is what we are going to see in this one. Okay, so okay, so okay, this is the okay we have okay, this is the MOSFET. So p n type MOSFET, because the substrate is p type, so there after inversion there will be a creation of the n channel. Okay, so initially when we haven't applied any bias at this point at VGS and VDS, we haven't applied any bias. Okay, initially there is a depletion region which is in the equilibrium. Okay, there is a depletion region at this point. This is because of the this depletion region at this in between the this part of the depletion region is because of the Fermi level mismatch phi ms. Okay, this is the because of the phi ms, the Fermi level mismatch between the metal and the semiconductor. Okay, this can be, there will be accumulation also, there can be depletion also, so that depends on the difference between the if it is positive or negative. Okay, and this is the VSB uh, application of the voltage at the body. And now okay, yeah, now this is the application of the voltage at VGS without when VSB is 0. Okay, VSB is 0. When we apply the VSB is 0, so there will be E phi s, the between this one, so that will be 2 phi p. Okay, at threshold voltage, that will be equal to 2 phi p. Okay, so the 2 phi p is, as I have been keep saying, that the 2 phi p is the difference between or the gap between the intrinsic Fermi and the Fermi level. Okay, so this is the 2 phi p. But after the as we apply the substrate bias, so that will modify the concentration of the electrons at this junction. Okay, as we apply the so it this will be equal to 2 phi p plus VSB. Okay, as we apply the that VSB is if the substrate is positive p type, substrate is p type, so this Vs minus Vb, this will be a so okay, the potential applying at is negative. Okay, VSB and VBS, so these are the conventions different books follow, but what we are saying is at this junction we apply a negative voltage, that's it. Okay, so it will modulate the threshold voltage of the of of the device. So the surface potential of the storing inversion at any point x will be modified by 2 phi f plus Vx. So it was initially it was like this because of the source drain voltage. This Vx carries the information of the source drain VDS voltage. Okay, this is because of the here at this junction it is 0, at this junction VDS. So therefore there will be a drop, VDS drop in the channel. So there will be how it is dropping, we are assuming that it is dropping linearly, so linear drop in the voltage. Okay, so there is Vx. So after the application of the voltage at the body, so it is modulate this the inversion surface potential is modified to the 2 phi f plus Vx minus VBS. Okay, V minus VBS is the negative voltage applied at the body. Okay, so in this is in the absence of the substrate bias. In the presence of the substrate bias, this is the modified potential of the surface. Okay, our surface is, I am saying, this point, the interface of the oxide and the semiconductor interface. Okay, the now okay, just a minute. Okay. Now what we can see, the modified charge density in the channel. Modified charge density, the charge density at any point in the channel Qnx is given by the oxide capacitance and the voltage, the modified voltage. Okay, this is 2 phi f plus Vx, this was initial, and minus VBS. Okay, so this is the voltage that we have applied. So initially the charge Qnx is given by this one. Okay, so qnx was given at any point was given by this equation, and now what we are including, we are along with these v 2 phi f minus plus vx, we need to subtract vbs. Okay, minus vbs, that we are doing here. Okay, this is what we are doing here. Okay, okay, I don't know what is happening. Okay, so now what we can see is, okay, leave. Now this is the modified one. This equation is the modified equation. Okay, now what we will see is the okay, the effect of substrate bias on the threshold voltage. So this is the id, this is the vth des, this is the in the linear regime, and vth, okay, threshold voltage is given by vth des after the, due to the substrate bias. Okay, due to the substrate bias is given by this equation. Okay, so we, after solving that equation from this one, from here, threshold voltage vd saturation, this is the saturation with th. Okay, this is the threshold voltage, this is the threshold voltage. Okay, this is the threshold voltage. After solving this equation, we will come to vth dash. Okay, and this is the final equation after the threshold voltage modification. Okay, so how much there is a shift? Okay, how much there is a shift? So after solving this equation, vth minus vth dash minus vth, we will find okay, this is the equation, the delta vth comes. Okay, so this depends on the on the on the oxide capacitance and dielectric constant of the semiconductor. Dielectric, this phi s, no, this epsilon s is the dielectric constant from the substrate. Okay, substrate or the semiconductor. Okay, and this is the doping of the semiconductor, that p region doping, not the n plus plus or n region. So this is the p region doping, the substrate doping, and this phi f is what, this is the okay, the gap between the intrinsic Fermi level and the Fermi level. This is phi f, twice of phi f. Then this is the body voltage that we are applying at the body, and minus 2 phi f. Okay, this is the threshold voltage. So if we are applying zero body voltage, so this will be what will come is, this vbs is equal to 0, this will be 0, the delta vth is equal to 0. Okay, now now we comes on the very most critical parameter, which is the threshold or subthreshold conduction. Subthreshold conduction, why it is critical is because whatever, okay, in our mobile phones or laptops and whatever device you imagine, there are billions, millions of transistors. Okay, which drive the processor, or which drive our everything, or LEDs or our screen. There is a back panel in our screen, so which is nothing but the transistors in the back panel. Okay, so the intensity of the light is controlled by the transistors only. So how much is the intensity we want to give? So if you in the mobile screens, now coming to the OLEDs. Okay, so there is kind of a perfect black. So how is it possible? That is because of the LED. Okay, that we are driving. We initially what was happened, there was a back panel of the white LEDs behind the screen. Okay, and there are and above the screen there are pixels. So liquid crystal display or whatever you see. So in that there is the intensity of the light, that back panel, we are not even touching the back panel of the intensity of the each LED was was not the each LED. There was a kind of a light source, complete white light source, and that white light source is passing through a liquid, and after that liquid there are pixels. There were many pixels, RGB, red, green and blue. Because of the combination of the RGB, we can make any combination of any light or any color. We can make any color. Okay. So so uh, before that, so there the light is controlled. So okay, there is a liquid. So we are we are polarizing the light through the liquid. We are controlling the intensity of the light through the liquid. Okay, by applying a bias at the liquid, we are polarizing the light. We are polarizing. When a light passes through a polarizer, what happens? The intensity of the light decreases. Okay, how much intensity of the light we want to decrease? If we want a zero light out of that, so so that is already say x or y plane polarized light is coming. So if the x polarize okay, if the light is coming in this direction, in this direction, so and the light is polarized in this direction. Okay, if if the polarizer is to, light will pass. Okay, light will pass. If the polarizer is like this, light won't pass. Okay, if the polarizer is, we have done at 90 degrees of the polarization. Okay, so the light won't pass, and in between these two, we can control the intensity of the light. Okay, so but nowadays what happens? We are removing the complete source, the white light source behind, and now we are going towards the mini LEDs, micro LEDs. Okay, so each micro LED is controlled by the FET. The intensity of the micro LED is controlled by the FET. Okay, this field effect transistor. So by the gate voltage, by the how much ever the much we apply the gate voltage, we can control the current flow through that, and with the current flow we can control the intensity of the light. Okay, so whenever we want to turn off the light, so we will just turn off the transistor. We will give the zero gate voltage. Okay, we will turn off the transistor. But if turning on the transistor is taking too much of the voltage, okay, so if the threshold voltage is too high, okay, let us say if the threshold voltage is too high, so what will happen is, so this threshold voltage will consume a lot of battery power. Okay, this threshold voltage will consume lot of your battery, of mobile battery, laptop battery will be drained very soon. So this is what this subthreshold conduction is very important. How fast our so how much minimum voltage it is taking to turn on the transistor. Okay, so in subthreshold in the okay, so this is okay, subthreshold condition conduction. Subthreshold conduction is okay, this is the linear graph, ID versus VG. Okay, with the application of the gate voltage, this is the ID versus VG. So after a threshold voltage, it starts conduction. Okay, after a threshold voltage, it starts conduction. So what is happening in this region? Okay, we don't know. So we how can we for that we will plot a log graph. So in subthreshold in subthreshold region, this is a weak inversion. Okay, this is the weak inversion regime, or in the strong invert, this is the strong inversion regime, this is the weak inversion region. Okay, so in the weak inversion region, so how this is like how much voltage this is taking to turn on the transistor. So this is the off voltage, off state, and this is the on state. So this much of the voltage it is taking to turn on the transistor. Okay, this is the threshold voltage. This much voltage it is taking. So if this is steep, okay, if this is more steep, this is the more steep, this sub-threshold swing, we call it sub-threshold swing. So if it is more steeper, so to turn on the transistor it is taking a very less voltage. Okay, so this is why this is very important. And and okay, in sub-threshold swing or sub-threshold swing, what so how much voltage, how much gate voltage is required to increase the current by a decade? By a decade means 10 times of the current. Okay, in this region, in this sub-threshold region. Okay, so and id is primarily the diffusion current in this region. Okay, okay, that is not that important. And another thing is the sub threshold swing, how sharply this id is changing with vg. How this is the how much steeper this is, how much steeper this is. Okay, if this device is much better than this device, okay, but there is a limitation. So okay, so we want subthreshold swing, this subthreshold swing to be minimum. Okay, so how much voltage is required to uh, change the current in the device by 1 decade? So we need very less voltage, least possible voltage, to increase the current by a decade. Okay, so we want this to be more sharpened and sharper. Okay, so and in low power application, this is critical. In low power applications are the driving of this screen. Okay, this is the low power, so the back panel of the FETs. Okay, so this is the low power application. Okay, just driving the back panel of the screen or these things, these are the low power applications. And this sub threshold swing. Okay, someone wants to join. Okay, let me see who wants to join. Okay. Now, okay, now, so this is given by this equation. The subthreshold swing is given by this equation: log of log ln 10 to the base e, log 10 to the base e kt by q, and 1 plus cd by cox. Cd is the depletion, this depletion capacitance, and cox is the oxide capacitance. And when, so this can be minimum, when this term can be minimum. Okay, cd by cox can be minimum. So cd by cox can be minimum, then only this term can be minimum. Okay, so okay, so this term is approaching towards the zero. This term can be 1 at minimum, that cannot be, but this ln 10 kt by q is equal to 10 millivolts per decade. This term comes this after calculating this at 25 milli electron volts or 26 milli electron volts, when you will calculate this will come 60 millivolts per decade. So below this AD is kind of not possible to go below 60 millivolts per decade in this kind of configuration, in this MOSFET configuration. Okay, MOSFET. But there are other configuration of the devices which are kind of the tunneling devices, tunneling field effect transistors kind of. So in those it is possible. There is research going on in these fields also, which is not commercialized yet, but it will be. Okay. Now, steep subthreshold transistor, TFET, or the tunneling field effect transistor. Okay, so in this one, okay, so okay, this is kind of the, we can say this, okay, this is the gate. Okay, gate, conduction band, valence band. Okay, huh. Okay, so because of the gate, okay, so okay, because of the gate, it is reducing the barrier. Okay, it is reducing the barrier here. Okay, because of the gate at this junction. So this is the tunneling field effect transistor. In tunneling field effect transistor, this is the energy band diagram, kind of band diagram. This is the conduction band, this is the valency band in the x direction. So with the application of the voltage, we can modulate this conduction band and the valency band. And after, as we apply, this is the p type, this is the n type. Okay, this is the p type and this is the n type. This is the spatial band diagram. Okay, this is the spatial band diagram, which is in this direction, in this direction, in this direction. Okay, so so as we apply the voltage in between source and drain, what will happen is, so these two come very close to each other, and there is available states at this level also. Okay, as we apply the gate voltage, so what will happen is there will be a tunneling of the charge carriers. The electrons will tunnel through the junction. Okay, so there will be the current will be because of the tunneling between this p type and the n type. Okay, so this device can turn on at with a more steeper voltage or steeper sub threshold swing. Okay, so but the current is will be very less, because this is because of the tunneling. Okay, that there will be a limit in this current. And in the MOSFET, this is the 60 millivolts per decade, but the current will be higher. So if we want a larger current, if our other device needs more current, that LEDs or these things, so which requires higher current for the intensity, for brighter light, so for that we need MOSFET only. But in MOSFET, it is kind of uh, a battery consuming. Okay, it is kind of battery consuming. Now so now let us come on the short channel effects. So now why uh, do we need to learn this thing is, uh, according to the Moore's law. So now we are scaling down the, we are increasing the density of the devices in a chip, right? uh, to miniaturize the gadgets. Okay, so this is kind of a laptop only. We are taking we can do anything in our mobile. Okay, we have laptop, we have memories, we have like in terabytes of the memories in very small chip. Okay, how this is happening? This is because of the smaller and smaller billions, millions, billions of the transistors we are keeping in highly dense transistor in a chip. This is because of that only. Okay, but when we are miniaturizing the things, miniaturizing the devices, so there are other effects come into the picture. Okay, so this, we are scaling down the parameters. Okay, and because of the scaling down of the parameters, there are certain effects come into the picture because of the short channel effects. Okay, these are the short channel effects, or the channel length L. The channel length is, we are decreasing. Because of that, there are other effects coming into the picture. Okay, so scaling is the process. Okay, scaling is the process how we are scaling the length of the transistor, width of the transistor, doping, all these things we need to scale, so that our device can work perfectly without degrading the performance. Okay, so this is the, like, we had this is the size of the transistor or the gate, or we can say the channel length. The channel length is decreasing, going down and down. Now we have around 4 nanometer or 5 nanometer of the channel length. 4 nanometer or 5 nanometer is very less, very less. At the atomic scale we are going. Okay, so at that point there will be this, the channel length, this we are decreasing too much. So whenever we apply a voltage in between these two junctions, there will be a current, so the channel is not turning off. So the device is not turning off. What is the point of having a switch then? Okay, the device dimensions are shrunk down to miniaturize the device. Okay, the source drain depletion width are comparable to the channel length. So if this source and drain channel length, drain depletion width are comparable, then there won't be, so whatever the charge come, there will be a very high leakage current at that point. Okay, so departure from the long channel device, because as soon as we apply the voltage, there is a what to say, there is a pinch off region. So pinch off, or so the long channel, okay, we are departing from the long channel because there are several effects are coming because of that drain induced barrier lowering. There are several and the gradual channel approximation fails. So whatever the equations that we have derived previously, they won't uh, be applicable in this case. Undesirable electrical behavior, so there will be like I just told you about the there will be a high leakage current. The device won't get turned off. Okay, VTH no longer constant with length, with channel length that we are giving. ID is no longer scales down with 1 by L that we have derived W by L relation, that will fail because that we have derived with the gradual channel approximation, that will fail. Okay, now ID will no longer saturate with the VD, because as with VD, as we apply VD, so this depletion region will increase and it will reach here, so the device won't even turn off. That the current won't even saturate, so there will be, it will so whatever the electrons here, they will swept away very high values with a very high velocity. Okay, so these are the effects that comes. Okay, so how do we scale? Scaling is done at a constant field scaling. So there are constant voltage scaling, constant field scaling, and this is the scaling that constant field scaling that we will learn. So scale all dimension and voltage is a long channel MOSFET, a long channel MOSFET, such that the internal electric field is unaffected. Okay, the internal electric field is what we are saying, the electric field at this point, that should not be affected. Okay, the electric fields should not be affected. Now the scaling, so 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 these are the things for the constant factor, constant electric field. So how the length will be scaled? Length will be scaled by 1 by k. Okay, 1 by k. K is the parameter how we are scaling, that scaling parameter. E we are not scaling because E we are keeping constant. D is the okay okay, what is the D? I think D is the, yes, D is the this no, this oxide layer thickness. RJ is the depth of the drain and source n plus plus region depth. Okay, that they, all these things are scaled with the k factor k, how we are doing. Okay, so this Na doping density in this region is increased. Okay, so that we can reduce this WD. Okay, this is increased so that we can reduce WD, but because of this increment, this threshold voltage will again decrease, will again increase. Okay, because this Na is highly doped. if we are going a higher doping, so this the threshold voltage will increase. Okay, so these are the effects that will come into the picture. So now but what we cannot do is we do not have the control over the thermal energy. Okay, we do not have control over the band gap of the, we cannot control these things. Okay, VBI and phi s for the onset of the inversion do not scale. Okay, these things or phi si, that the interface, okay, that semiconductor oxide interface, this thinner gate oxide leads to the leakage current. This is the problem actually. So if we will decrease the thickness of this gate dielectric, so there will be a tunneling in between the gate and this semiconductor. If the tunneling is happening, this is the leakage current. Okay, this is the leakage current, and source drain series resistance will increase. Because why it will increase? Because this Rj, we are decreasing the Rj with a factor of 1 by k. Okay, this will decrease. So and this will series resistance will increase, and channel doping can't be increased indefinitely as p-n junction breakdown. Okay, this channel doping, this is the channel doping, this is p. Okay, VDH can't be scaled as, and subthreshold swing doesn't scale. Okay, subthreshold swing, yeah. Okay, and okay, so if we are going okay, subthreshold swing cannot be scaled. So if we are applying a more drain voltage or more gate voltage, VTH cannot be scaled. Okay, so if we are applying more gate voltage, so there will be a very high gate leakage current. That is undesirable. Okay, VTH cannot be scaled because of the this thing. VTH cannot be scaled actually. Okay, now because of this scaling, so how if we are doing the scaling, this short channel effects are coming. So charge sharing between the source and drain, if we are decreasing the channel length, if we are decreasing the channel length, this channel length, this channel length, so there is a depletion region in this region and in this region. Okay, in this region it is high because of the VD applied. Okay, this is the high and this is low because this is a 0 voltage at this junction. So because of this, there is a this is the charge sharing by this one, what to say, this the source, and here the charge sharing by the drain. So if it is not that much effective if the channel length is high, but if we are reducing the channel length, then what is happening, this is this is comparable to the channel length. This length is becoming more and more comparable. Okay, so how much is the charge sharing, that will affect a lot of parameters. Okay, so threshold voltage, it will affect the threshold voltage. Okay, so we will see how much is the charge in this one. So this is the charge QB that is given by the charge in this trapezoid. Okay, this trapezoid. Okay, so this is given by L plus L dash divided by 2QG NAWDM. Okay, this is given by this equation. So L dash is nothing. L dash is nothing but the which is the reduced length because of the application of the drain voltage because of the depletion region. Okay, this is the reduced length, L dash. Okay, so how this threshold voltage is changing? So initially, so if we have the channel length is higher in this region, so that we can see in the higher channel length. Okay, so the threshold, this is the VD, so this is the threshold voltage, nothing but this is the threshold voltage, how the threshold voltage is behaving with the channel length, and and when VD is applied is equal to 0.1 volt only. Okay, so threshold voltage is becoming lower and lower. Okay, so but if we do not want the device to be turned on but it is turning on, this is the case at very at uh, very so in this case the gate leakage current will be higher. No, not the gate leakage current, leakage current between the source and drain will be higher. Okay, just a minute. Okay, so now drain induced barrier lowering, whatever the voltage we are applying at the drain, so at the drain, how for the short channels, how this depletion region is behaving with the application of the drain voltage, and if it is lowered too much, what will happen? Okay, so initially for a large channel, this is the large channel, so this is the application of the voltage, so whatever the electrons will be jumped through this one, so they will go through the channel. Okay, okay, so they will go through the channel, but if we are reducing the length very much, so if we are reducing the length till this point, so what will happen is, so whatever the voltage, whatever the electrons are here at this junction, they will can easily jump. So if we are applying a more VD, so we are okay, the bands are bending too much that it is affecting the source. Okay, so at this point electrons, we are turning on the transistor. Okay, without applying the gate voltage we are turning on the transistor. Okay, that we do not want. Okay, so here the majority charges will be okay, can be what to say, can be injected. Okay, these majority, as soon as they are injected, they are swept away because of the electric field, very high electric field at this point. Okay, so okay, so this is the case. Okay, and and in drain induced barrier lowering, what is happening in above threshold voltage, above threshold voltage, as we have applied the threshold voltage, this okay, okay, initially it was higher, so it is coming down after applying the voltage. Okay, so and after applying the drain voltage it is going a bit more down. So what will happen is, so electrons, as we increase more and more drain voltage, easily electrons can go easily, there is a continuous conduction. As we more the application of the drain voltage, more will be the current, so it is not saturating in this region above threshold voltage, or it is not saturating in this region. Okay, the graph should be like this, right, like this, but it is not saturating in this region. Okay, in subthreshold region, so in subthreshold region what is happening is, we are not even turning on the transistor is turned on. Okay, the transistor is turned on at minus volts, it is turned on. Okay, so with the application of the VD is 1 volt, which is constant. So we have applied the VD 1 volt at for the very short channel. For the very short channel, what to say, it is around 1.5 micron. 1.5 micron. The current is very high. Okay, the current is very high in this region, which is not desired. Actually, it is not turning off. Actually, the on-off ratio is nothing. On-off ratio is less than 10. Okay, so if we are using this transistor for to drive our back panel, our screen will always be on, it won't get turned off. Okay, so there are some undesirable currents, so because of the gate application. And another problem is, this is not a short channel effect, but this is common for the all the devices. What is happening, if we are applying a gate voltage at this point, so if the if there are electrons here, because if the field is too high, the electrons will go and impact. Okay, the electrons will go and impact the oxide layer, this oxide layer. Okay, they can create the vacancies, they can kick off the electron from here. And if the kinetic energy is too high, they can because energetic electrons in there, so while going this side, the electrons, because there is a field in this direction also, but we have assumed in the gradual channel application approximation that the field in this direction is very small. Okay, so because of that because of this field, the electrons can go in the oxide layer. If they are going in a oxide layer, they can do the have do the impact ionization can happen. And because of that, this they can trap the charge. Okay, this degrades the this oxide layer or the dielectric layer. This degrades the dielectric layer. Okay, gradually your device will go down. Your device will get damaged. Okay, so it won't be any in the working condition. So so it affects the lifetime of the gadgets, whatever we have, mobile phones, laptops, whatever. Okay. So okay, that's it for today. So thank you. So next time we will see, we will cover the another topic.